Thanks very much, Marie Razia. Thanks for inviting me here, and thanks to Thomas. I've had the pleasure of interacting with Thomas for a long time, and this is the title of my talk, The Impact of Alps in Accelerating Scientific Discovery. So let's move forward with this.
Oh, no, sorry, you have the...
Sorry.
Yes, with this.
Okay, great.
Sorry, thank you.
So this is a little bit of a dense chart, but it's a bit of a measure for how you make progress on scientific discovery. It's an evolving sort of activity. And so the so-called Scientific Discovery through Advanced Computing program is based on validated advanced scientific HPC codes that come out. And this graphic here shows how the different elements that are involved, applied math, computer science, together with various computational physics application domains, how this is all integrated, and of course big data is a key part of all of this right now. You come forward and you make computational predictions, and then you go through two different loops here. On the left-hand side is what we call the verification, validation, and uncertainty quantification loop. This is what keeps you honest in terms of deliverables that can be checked and cross-checked. In the bottom here, I said these are comparisons against fairly simple sorts of things like empirical extrapolations, but then to sensitivity studies and so detailed structures that are measured. And you keep on going through this until things basically respond well to this VVUQ loop. The other side is the performance loop. That's the practical side of things. How fast does it take? What's your speed and efficiency in doing these things? And this involves things like modern co-design challenges, like Thomas was mentioning. Also, basic sorts of things that you're always encountering, low memory per core, locality, latency, all these things that keep on evolving and changing. So you keep on going through both of these loops, the VVUQ loop and the performance loop. This is a never-ending sort of thing, because there will always be new tools for scientific discovery that are required. And you repeat this cycle as new phenomena are encountered. So you just keep on going on this sort of thing. And it's just great to see a fantastic new capability like Alps come into play, because this will accelerate discovery. This is fairly straightforward. I think most of you are familiar with this. This is what we call a AI machine learning HPC workflow. This is pretty generic because you basically identify the signals or classifiers off of which you make the predictions. These are correlated with measured signals with advanced diagnostics. The pre-processing and feature extraction is pretty straightforward. These involves measuring sequential data arranged in patches of equal length for training. You follow this sort of scheme so you avoid like a Tower of Babel situation. You have to have some way of normalizing things. All data should be placed on an appropriate numerical scale of order unity, database with AI-based signals divided by their standard deviation. And then that blue box up is the more complicated thing these days that you're encountering with AI especially. Challenges associated with hyperparameter tuning. I'm not going to go through all of this right here, but this is a pretty common sort of just regular deployment of things like before, long short-term memory sort of networks. You iteratively go through these through various epochs or equivalent of an entire data set. For each iteration, there are books written about this, the book by Francois Chollet that we teach in our classrooms. And you repeat this over and over again. You apply the machine learning, deep learning software on new data as you keep on going forward. And so what are some of the grand challenges that one interacts with? Harnessing the power of AI in scientific discovery. Right now, there's a lot of interest. You've heard a lot of discussion about power. The need for power. There's no end to that sort of capability, including when you bring a powerful capability like Alps into play, you still have to come up with power. And one of the grand challenges, of course, is delivering clean energy through fusion power. And so it's an exciting time for fusion as a final frontier of sustainable clean energy. Many people believe this. Nuclear fusion promises practically unlimited clean energy, and we are truly on the precipice of cracking this grand challenge problem. And this is a very strong international activity involving countries, friendly countries like the US, Europe, Japan, and so forth, but also those which we are intensively competing against, like in China and such. It would be great if things were more shared, so it's a small world. People should be working together and combining their knowledge bases. But in any case, you should look at what has been happening. The scientists in the US under the National Ignition Fusion Activity in Livermore did achieve a break-even ignition after almost 30 years of work in this area. But the challenge of extracting fusion power on the grid is a huge challenge that still has to be met. To many, myself included, we believe the faster track is through the magnetic fusion sort of approach. The so-called Eurofusion Joint European Tourist Team achieved a record 70 megajoules of fusion yield in 2023. This is real progress going forward. It's not, oh, well, let's hypothetically expect something to happen. Now, on the right-hand side here, these are the targeted activities. ITER, this big international reactor that's under construction and targets a first plasma. This has been delayed some, and the first plasma is going to be probably sometimes more in the 2035 range. But meanwhile, billions of dollars are currently flooding into fusion research from the private sector. This is both good and bad. The good part is that it generates a lot of excitement, and it really generates a lot of interdisciplinary interactions. But the sort of negative thing is you're subject to a lot of hype, over promises and such. And this is going to get to another thing. Remember, in that flow chart that I showed, verification, validation, and uncertainty quantification is a big deal. This you can't fake this. You can't fool Mother Nature. And so this is something that you have to keep in mind as you go forward. And so this is just an example of how we're deploying AI deep learning to deal with a tremendous amount of data that's been accumulated in the Joint European Torus, in the General Atomics D3D machine. This, I'm not going to go through details of this, but it's very well articulated in this Nature paper. But this is quite interesting. I won't go through the details of this diagram flow chart on the right-hand side, but one of the things that really is moving forward extremely rapidly is that you come up with surrogate models, okay? These are approximate models that must be validated constantly as you go through this. It's very, very fast, and especially when you're dealing with real-time challenges that NVIDIA is, of course, very interested in doing. They've been very supportive of our R&D in this area, and we've been really fast progress in this area with our surrogate models, where we've achieved inference times on the order of milliseconds, but more importantly, these surrogate models can deliver results 5 orders of magnitude faster than the parent high-performance computing code runs on exaflop supercomputers like Frontier et al. And this is another reason why we're so excited about Alps, because in order to actually deploy this, and to deploy this in real time on a real operating machine, this is where you can do some really cool things, because this now you see the relevance to other real-time activities like self-driving cars, drones, etc. It all becomes very, very interactive. It draws a lot of attention from the super bright younger people that come into the field, and it demands a different paradigm, if you will, of interactions between universities, labs, and industry, the private sector. So this is an example of some of what's coming out. This is an example of a fusion digital twin workflow. This is still very, very active right now, and it's another example of how we're interacting well with NVIDIA who provided us with the visualization tools that enable us to go forward with this. I don't have time to go through this, but this is an example of this tokamak digital twin, and if I had time I would show you the movies of how you deploy this. But see, you can see a little bit of that going through here. This is the Omniverse capability there. But this is the guideline that I really want to leave you with, okay? This is the great Richard Feynman, okay? And this is the quote that we always follow. He said, "It doesn't matter how beautiful our theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong," okay? And so you can cut through a lot of hype and baloney by following this guideline. So this is my last slide, okay? Clean energy fusion and climate are 21st century grand challenges, accelerated by multidisciplinary research, and Alps supercomputing capability will play a key role in all of this moving forward. Timely delivery of fusion energy on the grid will also, it will naturally interact with the climate challenges, weather forecasting and such, that we've been hearing about. Validation against large observational experimental databases for prediction and real-time control is obviously a major challenge. The real-time simulators that I've been talking about, where you can test these things in real live experiments, this is the way you have to do it. Otherwise, you just can't accept, people just saying, well, we're going to put power on the grid in 2 years or something. How are you really going to do it? What have you done to make us believe this? So first principles-based exascale simulations are very achievable these days, we believe. The Alps 5K Grace Hopper modules that you heard Thomas and others talk about, we're very excited about this. I've got some of our brightest young people very excited about getting onto this system. The industry engagement is very real. Microsoft's transformers, NVIDIA's Omniverse visualization that we've been utilizing to accelerate progress on digital twins. The essential role for AI is very clear. You absolutely need it for active control and design. You need to harvest cross-disciplinary things like the natural language processing and image recognition capabilities, for example, found in GPT models, and we call our own latest version of this Fusion GPT. There's lots of different things coming out, and it's a great way of attracting the best and brightest talent to the grand challenge growth areas. And the young people, they pick up things so quickly, and you can't fool them very much. They really know, because they have so many choices. And this interaction here between multidisciplinary R&D involving industry partnerships, this is really kind of a new paradigm for research going forward. It doesn't reside with the great universities like ETH Zurich, Princeton, Harvard, and so forth. It also involves the interaction with the labs, but also very much with industry. The young people very much want to have some experiences in working with the industries like NVIDIA. And it will require multidisciplinary R&D and strategic international collaborations. I don't have time to go through all of this, but I've had a lot of experience in the past, not just in terms of very productive collaborative interactions between Europe, the US, Japan, and so forth, but with previously presently unfriendly countries like China. And it really should open up things more. And I believe that a capability like Alps will help open the doors to some of these things going into the future. And I'm very excited about all this. So thank you very much.
Thank you. Thank you.